Hello, and welcome back. Today, I am very excited to finally be able to introduce the new topic we'll be focusing on for the near future, AI for video games. Earlier this year, around February or so, I rounded out the last bit of details in the physics engine to the point where I felt comfortable finally moving on to developing the AI and entity systems of the framework. I believe it was around March or April I began specifically getting into the AI side of things. And so I would like to make this note going forward. This is going to be more covering a work in progress. The physics engine was more or less complete for the purposes of what we were covering by the time I began that series. While I do have most of what I think will be the core AI architecture, I know there will be changes in the future, some of which I already have planned and I'm working out some ideas on fleshing out the final details of the system. Nonetheless, I hope you all enjoy this journey into developing an AI engine with me. I'll first start by just laying out a simplified visualization for the entire loop of a video game. You start with player response, go to input response, simulation response, render response, then you display the game, and we end up looping back to the player response based on the new frame. What we'll be looking at today is the simulation loop, and more specifically the AI portion. However, I think it'd also be good to get an overview of the simulation engine to see where these things are. And let's remember that the output of a simulation engine is a series of transforms used by the rendering engine. So starting out, the engine has the runtime database with the state table, the action plan table, and other auxiliary tables. It also has the simulation thread, render thread, and AI planning thread. As previously stated, the input of the rendering thread is the simulated transforms found in the state table. This data comes from the update of the transforms done in the simulation thread. This update occurs in two parts. The first is integration for our physics objects, and the second is action execution for our AI entities. And this brings us to our new topic at hand, the AI planner generating the actions to solve its desires, and these actions being executed by the simulation thread, with the downstream effects being displayed inside the render thread. And in order to do this planning, the AI thread itself also pulls various pieces of data from the database. As I previously mentioned, earlier this year I began looking into AI and the various techniques. Granted, I had some exposure beforehand, but no real study. During this, I found that there didn't seem to be a concise way to structure AI in the same way that you have, say, a rendering or physics engine. The techniques and concepts are well defined and explored, but I was unable to source anything that brought it all together in a seamless fashion, especially when you need to later integrate the AI into the rest of your framework. So I bring this up to say that I read a lot of media for AI about games, and everything did seem to agree on at least one point. The AI engine is simply interested in generating a series of actions that, when complete, will solve a set of desires currently held by the system. And I should mention that would actually only be for goal-based planning systems. Just goes to show how vast the subject is. So in attempting to achieve this goal, as well as craft a standalone engine that will encumber the other parts of the framework minimally, the AI engine itself will make minimal assumptions about the underlying data and functions it will be working with, and passing these responsibilities over to a Blackboard and something I call a Hivemind system. The Blackboard and systems are designed to follow a template to allow the users to add and remove the explicit data and functions required to solve desires. Subsequently, this means that each system must be appropriately designed to not rely on a system which relies on it. This then allows the action planner to work through each of its desires in a generic manner, unencumbered by the underlying requirements of the systems, or without needing specific knowledge about the types of data and goals to be worked with. Moving on to the specifics of the AI engine. Let's take a look at some of the supporting structures used throughout, starting with desires. Desires are a very simple structure. It contains information about the specific drone, if any, to perform action, the ID of the objective in the Blackboard, and it also has two descriptors, one about the system responsible for the desire, and another about the type of goal that the responsible system is to complete. And by the way, a descriptor is just a type def basically of a U8. Next are world states, and a world state is essentially just a dynamic type with enough storage to have a quaternion. The world state is a basic type used by the AI engine, and specifically objectives are an implementation of world state used inside of desires, or rather used when solving desires. So we'll take a look at action details and actions. The details about an action describe exactly how the system which performs the action functions. Actions themselves are a standalone function which follow the signature of bool, const u64, and data system, or takes a reference to a data system. Actions are returned by an action generator, which has the signature action, const objective, reference action. The action generator will fill out the details about the action system and type, as well as generate a lambda function to be executed on the simulation thread. Also, I should mention here that a data system is a basic type used across the rest of the framework. It's essentially, if you think about an ECS, it's where the components would be stored. The design for the Blackboard is still a work in progress, but here's the general concept for how I plan on it functioning for this AI engine. Bare bones, it'll have mechanisms for storing and retrieving object IDs and the primitive that represents them. These primitives are broken into the categories drone, construct, hazard, and location. To quickly define these terms, a drone is an object which has at least one capability in a Hivemind system. A construct is an object with no capabilities. A hazard is an object which, when planned against, is to be avoided. And a location is an object which, when planned against, is to be traveled to. These default primitives cover most of what I would imagine is found in a real game scenario. However, should these primitives not be enough, I plan on adding in a mechanism to extend the primitives. In addition to that extension mechanism, in order for the Blackboard to be useful, Hivemind Systems will be responsible for signaling to the Blackboard what data it needs to store and how to retrieve it. The system will also have to provide a mechanism for updating the Blackboard data that they're responsible for. In the code, these are still called agent systems, but that's a vestigial of the original design I had going on. I dropped the term agent in favor of drone as it's more reflective of what I believe the system is attempting to do. But for now, drone and agents are interchangeable terms if you see them. So the Hivemind system is a purely virtual interface. It provides all the functionality that, once implemented, allows the Hivemind Planner to solve its desires. Type actions, or get type actions, return the collection of actions that solve a certain desired descriptor, and these are known as goal actions. And translation is the process of a system taking in a desire and an ID and returning back the subsequent data field from the Blackboard for the objective. You can think about if you have a combat system, it might be interested in, say, the health of an object given an ID. However, it might also need to translate to that ID, in which case the pathfinding system would want to translate it and represent it as a position. So that was a lot of groundwork, and I think it's best to put it all into a demonstration on how these things are built and used. By default, the only Hivemind system that is packaged with the AI engine is the pathfinding system. Just about every other system that would extend into AI will use pathing in some form. However, I made sure to design the system as if it were any other Hivemind system to ensure compliance with the overall philosophy of the engine. At their core, The Hivemind systems are based on indices, and the goal indices dictate what generic goals the system is able to complete, while the capability indices dictate the permissible drone features the system has and which functions they may execute to perform the desired goal achieving action. Currently, the only goal that this system has is to translate, but at the end of this, I believe I'll be able to demonstrate how to easily make the system less rudimentary with minimal work. This is a little overkill. You really don't need all this, but as you can kind of see the idea here. In this example, the system works with drones who are capable of either being mobile, having the ability to fly, or having the ability to teleport. Looking out here at actions, this is where the bulk of the actual game-related work gets done. As you can see, the current system is beyond impractical, but it's more to demonstrate and at the time, prove the system would be able to generate the actions in the AI thread with the requisite data systems that are found in the simulation thread. In the future, this would actually be something more like generating a set of waypoints using a navigation mesh, and then passing that computed navigation data into the action planner via the action lambda for the simulation thread to work on. And this is still one of those things that are work in progress right now. I don't have a good way to standardize what I call satisfiers, but it seems to be largely irrelevant as the systems would need to implement specifics anyways. And this type of code is perfectly capable of being executed on the simulation thread since it doesn't interact with the state of the AI engine. However, in this example, the in-range function is acting as a satisfier to determine if a drone is in range of a specific objective location. And finally, wrapping up all our actions under one nice bow for our action planner is the goal actions. Goal actions are simply a set of related action details, any of which are capable of solving a specific system goal. I would like to show how these systems can not only be extended, but built off one another. Let's assume we have some other system or systems driving a guard type drone, and we want the guard to patrol some area. To achieve this, we could add a new goal index, and we'll call it wander, just to be a little more generic. Then we can create a new action, call it compute wander area, and we'll add in the new set of goal actions, calling them wander actions. Finally, to make these actions visible to the planner and get action types, we account for the new desire type. One more thing I would like to take a look at is something I call requisite actions. As the name suggests, these are actions which must be completed before the primary action is able to be completed. In this particular example, before the combat system is able to execute the planned attack, the pathfinding system must translate to the desired position. Skipping over the actual planner as it's more hacked together to get the action plans generated, there's still more supporting technologies, namely translation mechanics and Blackboard updates. Seeing as these are very critical to solving desires, I think it's best to move on from this for now. However, the planner itself will definitely have at least one video dedicated entirely to it, and more than likely a few. So currently the system is functional in a very, very simple way. In the future, I have plans to finish up the Blackboard changes as well as flushing out the actual planning. As for the Blackboard, allowing the systems to register data buffers as previously mentioned is a big one, as well as providing an updating mechanism so that the Hivemind systems can actually make use of the registered buffers. Specifically, what will be coming next is going to be an actual pathfinding system with proper nav mesh and pathing algorithms. That is about all for today. However, thank you so very much for your time, and I will see you in the next one.